In previous videos, we looked at how we can construct Hess cycles and use these cycles to calculate enthalpy change of a reaction using various enthalpy changes from other reactions. And these other enthalpy changes could have been measured by using calorimetry. In this video, we're going to look at different methods to working out enthalpy change of a reaction theoretically. This method uses bond enthalpy values, specifically mean bond enthalpy values, and we're going to look at why we use mean bond enthalpy values rather than just bond enthalpy values. We're also going to look at how we can use these bond enthalpy values to calculate enthalpy change of a reaction through a very simple equation. And we're going to look at some of the limitations of using this method to work out enthalpy change of a reaction. Before showing you how to use bond enthalpies to work out enthalpy change of a reaction, we need to define what we mean by bond enthalpies, or to be more specific, bond dissociation enthalpies. The word dissociate means to separate or break apart, which is the opposite of associate, which is joining together. Bond dissociation enthalpy is the energy needed to break one mole of a particular bond in molecules in the gaseous state. So for example, a particular bond could be the iodine-iodine bond, and this equation will represent the bond enthalpy for iodine-iodine bond, as we're breaking one mole of iodine-iodine bonds and the species are in the gaseous state. All bond enthalpies are endothermic, so they should have a positive sign. This is because to break the bond, we need to put energy in to overcome the attraction between the electron density between the two nuclei and the nuclei themselves. Some bonds can only have one bond enthalpy value. For example, iodine-iodine bonds can only exist between iodine atoms in iodine molecules. A hydrogen-hydrogen bond can only exist between hydrogen atoms in a hydrogen molecule and doesn't exist anywhere else. However, some other bonds can exist in many different types of molecules, and the environments in which those bonds are in those molecules can affect the bond strength of those bonds, and therefore we need to use mean bond enthalpy values for those type of bonds. So for example, if we look at the bond strength for a carbon-hydrogen bond, a carbon-hydrogen bond can exist in a number of different types of molecules. So it can exist in something like methane, or chloromethane, or dichloromethane, or in any of the numerous organic compounds that exist. So the bond strength of a hydrogen-carbon bond is going to be slightly different in each of these molecules because the other atoms around it will influence the electron density between the carbon and the hydrogen nuclei. So for example, if we compare the bond strength of carbon-hydrogen bond in these two molecules, the bond strength of the carbon-hydrogen bond is going to be weaker in this molecule compared to this molecule. And the reason is the chlorine nucleus has a greater ability to attract electron density away from the rest of the molecule. So the electron density between the carbon-hydrogen bond is going to be reduced because these electron densities are withdrawn towards the chlorine. So out of these three molecules, the carbon-hydrogen bond strength is going to be the weakest in this molecule because the electron density between the carbon and the hydrogen is going to be withdrawn towards the chlorine. So therefore, the electron density between the carbon and hydrogen nuclei is going to be the lowest for this molecule. So this molecule out of these three will have the lowest bond dissociation enthalpy for carbon-hydrogen bonds. So knowing that, we need to use mean bond enthalpies or average bond enthalpies when we calculate enthalpy changes of reaction using bond enthalpies, because there'll be a numerous number of different bond enthalpies for one particular type of bond. In some cases, for example, in the case of carbon-chlorine bond, there will be lots and lots of different values of carbon-chlorine bond enthalpies because carbon-chlorine bonds can exist in many different molecules. So now we know what bond dissociation enthalpies are and what mean bond enthalpies are. We're going to see how we can use bond dissociation enthalpies to work out enthalpy change of a reaction. I'm going to use an enthalpy profile diagram to explain how we're going to do this. So in any reaction, we have reactants converting to products. And in the case of an exothermic reaction, the reactants will have higher stored energy than the products. And to convert the reactants to products, we break the bonds in the reactants and put energy in to break the bonds, which will then form the intermediate or activated complex. And then new bonds are formed to form the products, and energy is released when new bonds are formed. So you can see on this energy profile that the enthalpy change of the reaction will be the difference between the energy needed to break the bonds in the reactants and the energy released when the new bonds are formed in the products. This value here will be the sum of the bond enthalpies of the bonds in the reactants, and this value here will be the sum of the bond enthalpies of the bonds in the products. So for enthalpy change of a reaction, which is the enthalpy change for the equation as written, we need to work out the number of moles of each type of bond that exists in the reactants and the number of moles of each type of bond that exists in the products. So we need to draw the bonds in the reactants and products to work that out. So here I've drawn all the bonds in the reactants and all the bonds in the products. So let's work out the enthalpy change of this reaction, which is 1 mole of methane reacting with 2 moles of oxygen to give us 1 mole of carbon dioxide and 2 moles of water. We sum up the bond enthalpies for 4 moles of carbon-hydrogen bonds and 2 moles of oxygen-oxygen double bonds to give us the energy needed to break all the bonds in the reactants. We then sum up the bond enthalpies for 2 moles of carbon-oxygen double bonds and 4 moles of hydrogen to oxygen single bonds to give us the energy released when the new bonds are formed in the products. We can see without having to learn an equation that this is going to be an exothermic reaction because I'm releasing more energy in forming the new bonds than I need to put energy in to break the bonds. Remember, we put energy in to break bonds and energy is released when new bonds are formed. So you don't have to memorise an equation to work this out in an exam. You know that when more energy is released than you put in, it's going to be a negative value because it's going to be exothermic. So you take away the big number from the small number. And if you put more energy in than you release, then it must be a positive number. So you take the small number away from the big number to give a positive number. However, if you want an equation, here it is. So in this case, taking the bigger number from the smaller number to give us a negative value, we get minus 806 kilojoules per mole for the enthalpy change for this reaction. And that makes sense because this is an enthalpy combustion of a fuel, so it should release energy. The most common mistake I see from students doing these type of questions is that they don't draw the diagrams correctly, or they don't bother drawing it at all, and they then miscount the number of moles of bonds in the reactants and the products, and therefore the calculation would be wrong. So make sure you count the bonds correctly. So there are 3 limitations in using bond enthalpies for predicting enthalpy change of a reaction. The first one is that we're using mean bond enthalpy values. We're using average values of bond enthalpies rather than specific bond enthalpy values for those specific bonds in the specific reactions. So for example, in the reaction we just looked at, the bond enthalpy for carbon-oxygen double bond will be different in different molecules because carbon-oxygen double bonds can appear in other molecules. So for example, we have a carboxylic acid with a carbon-oxygen double bond, and that bond strength here will be different to the bond strength here. So we need average bond enthalpies. Same with the OH bonds, because OH bonds can appear in other molecules. However, the oxygen-oxygen double bond will not have an average bond enthalpy or mean bond enthalpy because the oxygen-oxygen double bond can only appear in O2 molecules. So there is no mean bond enthalpy value for oxygen-oxygen double bonds because there's only one occasion where you can have oxygen-oxygen double bonds, and that's in O2 molecules. Another limitation of using bond enthalpies to predict the enthalpy change of a reaction is due to the definition of bond dissociation enthalpy itself, which is defined in terms of the fact the enthalpy change must be for gaseous species. So this means we can only predict enthalpy changes for reactions which contain only gaseous species. If there are species in other states of matter, we need to account for the enthalpy change when those states of matter changes occur. So in the calculation we did earlier to work out enthalpy change for this reaction, and we got the value of minus 806 kilojoules per mole, this value is actually incorrect because the reaction will produce water as a liquid, and using bond enthalpies we can only work out enthalpy changes involving all gases. So using bond enthalpies we actually predicted the enthalpy change for this reaction here where the water produces steam. So the enthalpy change for this reaction at the top here should be more exothermic because when steam condenses it will release more energy. So there's an additional enthalpy change going from this reaction here to this reaction here that we need to add using Hess's law. So really the enthalpy change for this reaction is minus 806 kilojoules per mole. And then we need to add this value of enthalpy of condensation from the steam to the water to give us the value here. So the overall enthalpy change here is the same as this enthalpy change according to Hess's law, because we start with the same reactants, end up to the same products. The last limitation of using bond enthalpies to predict enthalpy change of a reaction is the fact that bond enthalpy values are not determined under standard conditions. That's because we need to maintain all the species as gases. So for example, to measure the bond enthalpy of an OH bond in water, the water must be in the gaseous form, but water is liquid at standard conditions, because standard conditions is 25 degrees C, 1 atmosphere pressure, and in those conditions water is a liquid. So those bond enthalpy values are always for gaseous species, so therefore we may not be using standard conditions, and therefore using those bond enthalpy values we're not predicting enthalpy changes under standard conditions. So we can't use bond enthalpy values to predict the enthalpy changes under standard conditions. The value predicted will be very similar but won't be exactly for standard conditions. So we now covered the last part of the enthalpy changes topic, and we looked at how we can use Bond enthalpies to predict the value of enthalpy change of a reaction, which is a theoretical value. Using Bond enthalpies to predict the enthalpy change of a reaction will give us a different value to using Hess cycles, because the data we're using in the two different cases are different. And these will be different from the actual measured values using calorimetry in real life.